All right, well, thank you very much for the invitation. It's a great honor for me to be here. It has been a fantastic day and a half, learning a lot about the breadth of our field and all of the opportunities that we can have as we look into the future. So I'm going to switch gears a little bit from what you have been seeing this morning and talk about some engineering aspects of electrochemistry. And in particular, how can we bring electrochemistry to chemical manufacturing in the sense of transforming the way that we do separations or reaction engineering. But before I do that, let me just start by telling you a little about myself and what motivates me. So I come from Caracas, Venezuela, which is this beautiful country in South America. We got wonderful beaches in the Caribbean. We got the Amazon. So we have plenty of natural resources. And one thing that people don't realize is that we also get really tall mountains. And we have glaciers, even though we're in the tropic. So this picture is of myself and my sister maybe 25 years ago eating snow in one of the tallest peaks in Venezuela. So it's like more than 5,000 meters of elevation. But the sad part is that we're very rapidly losing these glaciers. So 25 years forward, there's really not much snow left in Venezuela, and it's kind of sad to think about a future in which I wouldn't be able to bring my kids to eat snow in one of these peaks. And it's probably not because we ate the snow that this happened. It probably came because of the fact that really close to that part, the Lago de Maracaibo, we keep extracting this wonderful resource, as Tom said, that help promote our development as a country and as a world, but inadvertently cause significant environmental issues. We heard yesterday a lot about opportunities for electrification in particular because nowadays solar and wind energy are starting to become some of the cheapest ways to produce electricity, in particular when you look at sunny places like where I come from, where you can produce electricity quite inexpensively, but these are intermittent sources of energy. So if you apply this to commercial residential applications where people decide when to use energy, and then the sun decides when to supply it, you have a mismatch. And this mismatch creates significant issues, which is why you see a lot of people working on energy storage. And it's exciting to see a lot of work going into transportation fuels to be able to clean up that aspect of our economy. So in my group, when we started 3 years ago, we decided to look a little bit more broadly and look at our industry from a different perspective and try to understand how can we bring electricity to our industry, the chemical industry, into multiple sectors. And yesterday, in the organic electrosynthesis session, we saw a lot of opportunities on this end, like pharmaceuticals or perhaps specialty chemicals, things that are really high value and reactions that are very difficult to make otherwise. But there's many other opportunities all throughout, right? And the idea here is to figure out a way in which we can go from the classical chemical production plant scheme to something that looks more like this. Where solar cells can drive these small electrochemical reactors, such as the one that Tom showed yesterday. So in this way, chemical manufacturing could perhaps become an enabler for deeper penetration of renewable energy. But to do that, we have to really focus on big volume chemicals. And in particular, I'm talking about basic chemicals. These are chemical commodities, the things that lead to pretty much all the materials and chemicals that we use today. So in my presentation today, I want to be focusing on some of the opportunities that we have there, and I'm going to just use petrochemical derived products as an example. And when we think about oil derived products, oil gives us a lot of wonderful things that we obtain through refining, all of the fuels that we use to run the world, but also provides us petrochemical feedstocks. And these petrochemical feedstocks are then sent to petrochemical plants where we make our polymers, our intermediates, our adhesive, and roughly about 5 to 20% of every barrel of oil that we refine away gets transformed into these feedstocks that then become the chemicals that we use today. But something interesting is happening that as we go towards an electrified economy and we stop using fuels as intensively as we were before, newer refineries are starting to be designed so that a much greater fraction of these resources are driven towards petrochemical production. So as newer refineries are starting to produce roughly 40 to 50% of petrochemical feedstocks, then go into a variety of processes. So the question here is, how can we go from the status quo, where we use heat, usually derived from fossil fuels, to drive our reactor units or our separation units, usually distillations, to something that looks like this, where you have electricity-driven processes that can come from renewables or other sources from the grid, and then our chemical plant starts to play a much more significant role into electricity generation, buffering, and whatnot. And here we really have to think about each of the units that are important. So first we have separations, as I told you before. We have to figure out a way in which we go from distillations to things that are electricity-driven. So membranes are a big opportunity. They're not necessarily electrochemical processes, but there are some electrochemical opportunities here to play as well. Reactions are clear. We have to figure out a way in which we can go from thermochemical reactions to electricity-driven reactions. And then we also have to think about energy recycling. So chemical plants are deeply integrated systems where energy is shuttled from one unit to the next, and you try to operate as efficiently as possible. So when we think about electrochemical plants, then we really have to think about cycling chemical potential in these systems. So I'm going to start by talking a little bit about some opportunities and separations, and then I'm going to focus much more on the reactor end, which, as we heard yesterday, is sort of the core of most of the processes that we do today. So in terms of separations, arguably, this is one of the biggest opportunities, right? So about 10 to 15% of the energy in the U.S. is used for chemical separations. This is huge. A big part of it goes to refining operations, and most of it goes to, production of olefins that we use for polymers, ethylene and propylene. So to put it in Tom Jaramillo's units, this is 30 kilograms per person per year. So it's a lot of plastics that we produce, and this is another big challenge that our community, chemical engineers and chemists, face as well. Most of these processes are done through cryogenic distillations, which just the name sounds very difficult and energy intensive, right? And I think we can probably do better if we transform these distillation units into something that looks like a battery of electrochemical reactors. So this is not a new idea. So Carl Cobals and collaborators in Colorado earlier in the 90s started looking into electrochemical cycles to promote separation. So this is what I call an electrochemical swing absorber model, where you start with a molecule that has a high affinity, like copper-1, towards an olefin, and then you oxidize it to copper-2 when it releases the olefin. So you can send perhaps a feed into an absorption chamber where you have copper-1, and then you desorb it upon oxidation on a different chamber. And in this way, you can purify gases. There's, of course, a lot of transport issues when it comes to this, because usually when you think about these electrochemical cells that are run in aqueous electrolyte, the solubility of these gases is quite low, so you really have to think about the reactor design that goes behind operating these at really high throughputs that you need for production of olefins. Also, copper tends to poison with sulfur, and so does silver, which is another molecule. So about 2 decades ago, a group in Exxon discovered this set of molecules, nickel dithiolines, which can very selectively bind olefins. So I think there's big opportunities for organometallic chemists to design systems that are reversibly, that can change reversibly their affinity towards olefin versus parafilms, and then develop in this way these electrochemical swing absorption systems. So I told you a little bit about olefins. There's other big separations that can use similar methods. So for example, CO2 capture is one of them. I think the group of Alan Hatton have been developing beautiful work around these redox absorbers that can selectively capture CO2. And you can imagine having a very similar cycle that can take fairly diluted streams to more purified streams of CO2. And I think another big challenge that we have as a community too is to think about separations that have to do with water purification. And here electrochemistry already has an impact. So we have commercially available electrodialysis systems. They are energy intensive. There is a lot of opportunities there in terms of reactor design, in terms of the membrane design, and in terms of our understanding how can we bring the energy intensity of these processes low so we can actually provide water to the world. So these are some challenges, opportunities. My group started to work a little bit on the olefin end. We were very early on, so I won't really share much results on that end. But as we move to the reactors, there is many other things that we can do. And let's go back to our petrochemical case study and then start thinking about which materials can we start playing with. So when we think about petrochemical feedstocks, we're usually talking about light olefins like ethylene, propylene, which we commonly associate with the production of plastics. But we also have aromatics. And these things not only produce plastics, but they produce a whole bunch of chemicals. And this is by no means an extensive list. And then the question is, how can we start thinking about electrifying our industry and identifying opportunity points? The first thing that you do is you try to understand which ones of this process could you possibly do electrochemically. And the answer is actually many of them, because they involve either oxidation, reductions, oxidative reductive couplings, or halogenations. And there's a lot of opportunities. Then the question is, where do you go? Well, you can get some guidance in terms of the volumes. So there's a lot of volume that goes into ethylene-derived products. But there's also a fairly large fraction that goes with our aromatics. And then as you go from left to right, then you add value to these molecules. So for example, if we look at ethylene, there's a lot of things that you can do. So of course, a lot of it goes to polyethylene, and I don't really think that we have a significant role to play there. But in many of the other transformations, we can actually play, like for example, in the production of epoxides, and I think you'll hear more from Kartish later today, where oxidation or selective oxidations can play a very significant role to produce high-value materials. But you also have things like halogenations. When you look at aromatics, you have a wide variety of reduction or oxidation methods, couplings. You can do halogenations that can lead to very high-value materials. So the challenge here as a community is to start thinking about how do we develop general design guidelines for electrochemical processes that we can then apply one reaction at a time, so that we are electrifying progressively our industry, starting from the biggest opportunities and going up from right to left towards the bigger processes. In my group, we have been focusing a lot on this molecule adiponitrile. And the reason for that is because this is a really high-value molecule that is used to produce nylon 6,6, which I'm sure you're all familiar with. So in this graph, I'm just showing you the value per kilowatt hour. So this is work from Eric McFarland's group that shows a lot of products that can be produced electrochemically or are produced electrochemically. And as you look down here, you have your things that are fuels. Those are fairly low value per the energy that you will need to produce it electrochemically. So if you were to pick a process that could perhaps have an impact, or just to think about it in Phil Baran's term, a forcing reaction, you probably want to look up. And these are actually not as high as pharmaceuticals, but they're starting to be quite interesting. Adiponitrile, for example, is not $50 to $1 per kilogram, it's $2 per kilogram. So that gives you a space to play and start to think about how to do that. So as I told you, this is central to production of nylon 6,6. From adiponitrile, you can produce hexane methylene diamine, or HMD, which is this diamine that can then undergo step growth polymerization to produce nylon 6,6. And another reason that we decided to focus on this reaction is because this is actually produced electrochemically today. So about 30% of the nylon of the world uses this molecule that comes from this electrochemical process that was developed by Manuel Beiser back in the 60s. And this is really high volume. So this is largest organic electrosynthesis reaction on Earth. It's carried out in plants that look like this. So this is the only picture that I could actually find from that plant. And you produce adiponitrile at scales of 500,000 tons per year. So not insignificant. And when we started to look into this reaction, we realized there's actually not that much academic research done on the reaction engineering aspects of this. And we started to look a little bit deeper into what happened in these type of reactors. So these reactors are undivided cells. So you use a cadmium or lead cathode, which I call an anti-catalyst, and you use that to avoid hydrogen evolution because you have an aqueous electrolyte. So you have an aqueous electrolyte that contains phosphate salts, EDTA, tetraalkylammonium ions, and water, of course. And then you disperse your organic phase into this aqueous electrolyte to bring your reactants and then to collect your products. The reason that you use water is purely practical. You could perhaps use organic solvents, but then the cost will be prohibitively expensive. So you really are stuck with water. And usually when you think about electrochemical processes at scale, what you want to do is you want to have high selectivity, high throughput because you want to use your capital as efficiently as possible, and you want to have high energy conversion efficiency because also you want to use your electron as efficiently as possible. So these are general goals of pretty much all of the electrosynthesis that you can think about. And there's some general challenges to organic electrosynthesis as well that this reaction faces. First of all, if you deal with water, which you kind of want to do, then you're limited by the electrochemical stability of water. So there's a lot of opportunities that come into play on how to control that from the catalysis endpoint. The solubility of reactants is quite low, which means that you're going to be limited by the throughput that you can produce in your reactants because you need to bring enough reactants to the electrode to be able to produce a lot of it. Selectivity is a challenge because as soon as you inject an electron or subtract an electron from an organic molecule, then these things can actually do many things. And in the context of adiponitrile, this is what it actually looks like. So you can start with acrylonitrile and make a dimer, adiponitrile, but if you don't have enough of it around, you can actually get hydrogenated to propionitrile. If you have too much of it around, you can produce trimer or polymers of this molecule that you don't want. then you have water, you can also evolve hydrogen in this reaction. So my student Daniela Blanco, who started with me 3 years ago, have been looking a little bit more deeply into these reactions, starting by looking at what is the role of the electrochemical environment around the electrodes to promote selectivity and then promote high production rates. And what we have been learning, or basically relearning, because probably people that have practiced this for decades in industry know this already, is that, well, you need supporting electrolytes to be able to carry charge. These are buffers because you sort of want to maintain the pH of this reaction. You have to have EDTA because usually when you have these electrochemicals that are undivided, your anode can corrode and those things can plate in your cathode, and that changes the selectivity of your reactants. Then you use these tetraethylamine ions which enhance selectivity, and they do so by going to the electrode interface, blocking water from penetrating there, and enhancing locally the solubility of your organic reactants. And overall, you need to maintain an intermediate pH, because if you go too high in pH, then you produce polymers, which you don't want. And if you go too low, then you produce a lot of hydrogen, which also eats up your electrons. So overall, by doing a fairly systematic study on the electrolyte, we were able to find conditions that led to fairly high selectivities, which are starting to approach those reported in this electrochemical process in industry. What we also found is that as you increase current density, of course, the selectivity towards the production of your dimer goes down, and the production of the hydrogenated version of your monomer goes up. So this hints towards mass transport limitations. You're not able to bring enough acrylonitrile to that interface to be able to dimerize it. And we started to wonder, how can we enhance the transport of these reactions? And then we just use an old trick in electrochemistry, it's pulse electrosynthesis, where we can apply a pulse, where we do a cathodic reaction during a certain time, we produce the molecules that we want. As the reactant starts to deplete at the interface, then we stop the reaction, and then we allow the reactant to back diffuse. And in that way, we can control the concentration at that interface. We can use continuum models to guide us onto windows of time frames in which we can control this concentration, and then we can run these reactors under dynamic conditions. And these are sort of the results that you get. So this is adiponitrile production as a function of cathodic times and a function of resting times. And what you can see is that as you go to the right, to higher cathodic times, your electrode is active for a larger fraction of the time, so you produce more adiponitrile. For most cases, you produce less than in the case of DC, because your electrode is not active 100% of the time. But for some cases, you actually enhance the production rate of adiponitrile. And the reason for that is because you enhance the selectivity. So you reduce the production rate of your hydrogenated product, propionitrile in this case, and in that way allows you to reach a 20% improvement in production rate of adiponitrile and a 250% improvement in selectivity by controlling dynamically what is happening inside of your electrodes. So this is a classical reaction engineering trick to something that have been already discovered in terms of the catalysis and in terms of the chemistry. So we did a lot of continuum modeling trying to understand what's happening at the interface, but it's kind of complex. Like, it gets you to a window of times that are relevant. And here's where I think data can really help, because we can learn from what the experiments are telling us, and then just by using regression models like artificial neural networks, we can develop predictive tools for the production rate of the molecules that we want, adiponitrile, based on some of the parameters that we had identified that had a high effect. In this case, cathodics and resting times. And the way that this looks is that we take the data, we train the networks, and then we can generate predictive tools that allow us to go to conditions in which we can optimize the process. So if you put all the data that we had collected in terms of the cathodic time, resting times, and production rate of adiponitrile, here's your point of 20% increase of production rate. We can fill the rest of the space using these predictive tools, which showed us regions in which we can actually enhance the production rate of adiponitrile. So Anila went back to the lab, ran the experiment, and then we actually further enhanced the production rate from 20% to 30% increase. And we do that by further enhancing selectivity. We lower the production rate of propionitrile as we increase the production rate of adiponitrile. So this is an example of how, by looking at an old process, we can learn what industry have developed empirically for a long time, and how to improve upon it using modern tools that we have at our disposal today. And this underscores a general way of doing research, because now you can go, for example, to Phil Baran and tell me, give me another reaction where you know a little bit about the mechanism, or you can perhaps go to Tom and ask him to give us another catalyst. And then we can think about how to control the environment around that catalyst, so we can actually push the selectivity towards production rates and selectivity values. They're starting to become relevant And when we talk about this, we have to worry about the electrolyte. This can be liquid electrolytes. There's a lot of opportunities in solid-state electrolyte where we use polymers at these interfaces with catalysts to drive selectivity, as we saw earlier this morning. And then we can think about what is happening inside our reaction or at our electrode and control those operation conditions so we can then push even further the production rate. And at the later stage, once we have deployed all of our electrochemical knowledge towards improving these processes, we can then rely on data analytics to teach us those things that we don't know, that we cannot predict later on. So this also underscores a set of tools that are needed for this. So we don't necessarily play in this space, but there's a lot of opportunities for discovery of new reaction pathways for those big chemical processes that I showed you before. We need to understand the mechanisms, and we need to understand what is the role of the catalyst, so we can then go and understand how to formulate an electrolyte, how to develop ion-conducting polymers that are geared towards those particular products, and how can we tune that electrical double layer so we enhance selectivity. And then we can start to think about reactor design and reaction engineering tools to be able to balance transfer process and kinetic processes so we can push the limits of our reactors. And then later on, using either automatization of our reactors, we can collect significant amounts of data that can actually teach us those things that we don't know. And I think there's a big opportunity here, not necessarily for big data, but for small data, because sometimes it is very difficult to collect experimental data in our systems. And if we can mix modeling with data to be able to move much faster, we could actually accelerate the transition towards this electrified chemical industry. So all across the scales, we rely on a wide variety of multi-scale tools, as I was talking with Esther yesterday, not only on terms of theory and simulations, but also characterization, that allows you to look at processes that are relevant in the length scales and time scales that we care about. This also calls for a change in paradigm in which we educate people. So I'm a chemical engineer by training, and this is pretty much what I've done all my life. We train our chemical engineers to think about reactor design, usually using this book from Scott Fogler, but there's really not much information about how to design an electrochemical process. So there's a need to build a bridge between the electrochemical community and the reaction engineering community. So this is not only in terms of knowledge, but also in terms of tools. So in my lab, we use a variety of tools, going from microfluidic devices to really look what happens at that electrode interface at the mesoscale, and then scaling up all the way to electrochemical stacks that can produce things in the orders of kilograms per day, right? And we understand everything that happens inside there, so we can actually intensify these processes, and then we can enable companies, such as one that we created, Synthetics, or other ones that others, like Tom's students, Opus 12, or Dioxide Materials, that are trying to bring advances to CO2 reduction into these type of systems that we can then deploy at a much larger scale, as I said, one reaction at a time. So we're very serious about this, and thanks to NSF, now we have a planning grant to try to bring these efforts together. And we're trying to do this as an open effort in the community. We don't have a team, nor we have a problem. We're going to industry to look for inspiration in terms of opportunities of some of these reactions that we could perhaps tackle, and then going to you, the community, to look into teams that can perhaps play in the component space, and we're talking about electrocatalysis, membranes, the unit space, reactions or separation units, but also bridge the gap between us and electrical engineers, because we need to be able to figure out how to integrate electrically all of the chemical plant and how to integrate them with a grid. So we're trying to do this through an open call and then through an ideation process where we bring all the community together towards convergence on this space. And with that, I'll just close by thanking my group, in particular my PhD student Daniela Blanco, who have done a lot of the work that we have, and some of the people that have supported it earlier on in this process. And I'll take any questions. Thank you.
Floor is open for questions.
You mentioned the big data and machine learning, and you said, oh, it allows us to these are modern tools to understand what was not already known. But it's not clear to me if it's just for pattern recognition, or if you really discovered new descriptors, new key concepts that were not known before.
Yeah, I mean, I think an example that I show you is purely reactor optimization. But I do think that there are opportunities to do discovery and do really fundamental science using machine learning. Because if you think about how we tend to do science, we fix all of the parameters and then we change one parameter at a time and then try to understand what that thing does to your system. I think here really, machine learning tools can really help you accelerate that process so that you can learn the key aspects of your system with less data. And that's why I said that I think the opportunity is in the better use of small data together with statistics to really learn and accelerate the way that you do research.
Hi, Alex Parra from Pine Research. A great talk. My question has to do with you were using a pulse technique in order to, I guess, improve like the yield and distribution of products. Just thinking back yesterday about some of the organic electrosynthesis type of reactions, like most of those reactions were either done in like a galvanostatic mode or a potentiostatic mode, where you just hold a constant potential, and those are done in like just reaction vessels. So I guess my curiosity is about, is the use of the pulse technique mainly because you have these stacked like fuel cell stacked cells, or is there like a fundamental chemistry reason why a pulse technique would give you a different like product distribution? Yeah, so it's not because of the stack. Like what I showed you actually was bulk electrosynthesis at one electrode, and it doesn't change the chemistry. What changes is really the concentration of the different species that you have in the region in which chemistry happens, and that really helps you drive different reaction rates towards different pathways on your reaction mechanism. So the chemistry is set by whatever is happening, but what we're tuning really are reaction rates. Okay, thank you. Yeah.
So you started to talk about separations, and that's an area that has a lot of promise here. So can you cite some examples where you've seen success in transforming the classical thermal approach to separations to an electrochemical?
So, I mean, I think there aren't that many examples. This is a nascent field. I show you examples from the literature. I mean, I think in terms of separation, the only commercial systems that I can think of are electrodialysis. As I mentioned before, we're not in a vacuum. There's different ways that you can electrify the chemical industry. I think membranes have many other opportunities. I think mixing what have been learned in membrane separations with some of these electrochemical tools that can facilitate transport through membranes can really get you further. Yeah.
So I want to follow up comment on that, on the aspect of membranes. With respect to both this and actually Tom's presentation yesterday. And one glaring hole I see in the discussion we've had yesterday and today, there is no talk about solid-state electrochemistry. I haven't seen anything regarded to that. There's solid-state electrolysis cells for oxygen production and hydrogen production for basically using for CO2 reduction or hydrogen, et cetera. There's membranes, ion transport membranes that are mixed protonic electronic and mixed oxygen ion electronic. Those high-temperature processes actually would incorporate better into existing thermochemical plants today than some of these other things, which, again, they're wonderful. Love them. I want the whole electrosynthesis. But it's an aspect of when do these things be deployed, and it's been discussed before, is scale. So those types of technologies can actually scale with existing chemical processes, not just necessarily being something of the future. And in that regard, I mean, we talked about sensors earlier. Actually, Shelley mentioned that. You know, what is the biggest sensor out there? We all have one. It's the oxygen sensor in our automobile exhaust. And it's probably done more to improve the efficiency, the fuel consumption of internal combustion engines than all of the battery electric vehicles on the road today. Wasn't discussed. That technology can be made more selective to speciate gases like NOx and CO for combustion, but it can be used for other chemical processes where you would be able to control better those processes by developing electrocatalysis of those types of electrolytes. Again, saw the battery work, great stuff. You know, Stan and Esther, my friends, are talking about things like making better cathode materials based on improving the voltage and capacity. But what about the ionic and electronic conductivity of those materials? If the cathode was not only higher voltage and higher capacity, but had ionic and electronic conductivity, you could get rid of all of the rest of the material in the cathode and really have a major step change in the energy density of the cells by just having an all-solid-state cathode material with respect to whatever's on the electrolyte. So really, I do think it's quite important that solid-state ionics is part of whatever comes out of this, and I have not yet seen that in the discussion. So that's my 2 cents.
Yeah, I mean, I couldn't agree more. I actually annoyed my student last night and asked her to send me slides about this, and I just didn't have time to talk about it. This doesn't make any sense with solid-state ionic. This is how it was developed 60 years ago. What we're moving forward is to have membrane-separated MEA-type devices where you send organics on one end and then something else on the other end, so you can actually couple processes. And I think there's a big opportunity there, because even though we have membranes, what we have started to see is that as soon as you go to these more complex chemistries, the transfer properties of this membrane change completely. So it's a whole different design space that you need to explore when you start thinking about ionomers.
Thanks very much. Let's thank again Miguel.